So cluster states are, well, states on a grid of qubits, and they have been entangled in a certain way. And now you can play with that. You can do certain things with it. So for example, the entanglement in those states is such that you can create a Bell state between any pair of qubits that you like, just by measuring other qubits in the vicinity. You can make a channel like this, okay, and you can create a Bell state. If you're so inclined, you can also create many. You can do other things. You can measure a bunch of qubits in this grid, and the remainder ends up in a surface code. There's also something you can do.
Can I ask the first question?
Yes.
In the previous transparency, so if I measure, so I understand Z and X stand for what I measure, but the result is random.
Yes.
So what do I do with this?
Yes, good question. It is like in teleportation. So you will get 1 out of 4 Bell states, and which one it is will depend on what these measurements are. So there's a simple computation on the side that you would have to do. It would be taking parities of measurement outcomes, and so you will, all those many measurement outcomes will condense into 2 bits, and those 2 bits would specify which Bell state you got.
Thank you.
Very welcome. Thank you for the first question. Good. So so this is stuff that you can do, and then the question is, how far can you take it? How far can you take it? And arguably, the most interesting application is computation. By other measurement patterns, you can imprint a quantum computation on such a resource state. In fact, you can implement any quantum computation on such a resource state. The scheme is universal. And the universality proof is what I want to talk to you about today, after we go through some introductory material. Okay, I should say this was in 2 dimensions. Now you can take it to 3 dimensions. Consider 3-dimensional cluster states, and what you're getting out of that is fault tolerance. You can build a fault tolerance scheme of quantum computation out of that. And we will talk about that as well, and it's coming up in the next lecture. Okay. And so here's an outline for this mini-series. So today is the introduction with the universality proof, or let's say parts of the universality proof. As I already said, next time we talk about fault tolerance. And then in the 3rd class, we have a subject at the intersection between quantum computation and condensed matter physics. Computational phases of matter is very closely related to symmetry-protected topological order. So we see what we can learn about quantum computation by considering symmetry. Yeah. Okay, so this is the outline for my contribution to the winter school. And here's an outline for today. So first, measurement-based quantum computation in a nutshell. Yeah, so we go through some elementary features of measurement-based quantum computation. I define cluster states and briefly talk about 2 early experiments. And the main part of the class today is the universality proof. I will show you what is to prove. Well, we will do a mapping to the circuit model. We will not be able to go through all the steps, but hopefully you get an idea of what is to do. Okay, so that's the plan for today. Before I begin talking about measurement-based quantum computation, just as a general reminder, there's 2 evolutions in quantum mechanics. There's, of course, unitary evolution according to the Schrödinger equation. That's one extreme. And then you have measurement, projective measurement. That's the opposite extreme. It's very different, but also happens in quantum mechanics. And unlike in classical physics, measurement is a process that changes the measured state. Okay? So just to pull out some features here, unitary evolution is deterministic. Measurement is probabilistic. You can never know which outcome you got. Unitary evolution is reversible. You can, in principle, always undo it. With measurement, you can't do that. Measurement is irreversible. Okay, so just kind of to see that these are kind of extreme poles of evolution in quantum mechanics. But it turns out you can build quantum computation on both of them. And when you build it on unitary transformations, then you're talking about the circuit model. And if you build it on projective measurement, then you talk about measurement-based quantum computation. And that's the subject of today. Good. So here is an overview of what's happening. So here we see our two-dimensional resource state again. So every dot and every arrow is a qubit that is being measured. And we'll talk about these different symbols in a moment. Okay, but first, the kind of overview things that need to be said is that if we have the right resource state to begin with, for example, a cluster state, then we can make universal quantum computation out of it. Not every state would allow you to do that, but the cluster state is an example of a state that has this property. And then about the scheme, information is now written onto that state and processed on that state and read out from it again solely by performing local measurements. There's no unitary evolution taking place. That's the computational scheme we're talking about. Let's go a little bit more into this plot, because this will be relevant for the universality proof. So, as I said before, we want to simulate a quantum circuit, and you can see the circuit kind of arising. So, what you would do with your two-dimensional cluster state is you would put the quantum register here vertically on the vertical axis, and the horizontal axis would become the simulated circuit time. So what is stretching out here on this cluster state is a circuit, a simulated quantum circuit. And you imprint that circuit by the measurements, specifically the measurement bases. Yeah? You can choose the measurement bases, not the measurement outcomes, but the basis is enough for defining the circuits. And so you see dots. Dots represent measurements in the eigenbasis of sigma z. And as it turns out, they have the effect of removing those qubits. It's as good as if they had never been there. And then you see, oh, once those qubits are gone, what you're left with is a circuit, a circuit-like structure. Okay? And along this circuit, so this upward pointing arrow represents a measurement in the x basis. Would just be there to shuttle information along, or so this up here is a wire, and this is a wire, and this is a wire just shuttling along qubits. And then you have these bridges, and these bridges represent interaction. So this is how you would do a CNOT gate, for example. And then you, of course, have the choice to change your measurement basis. For somewhat away from the sigma x axis towards sigma y. And there's an angle involved, and that gives you 1 qubit rotations. And so this is how you simulate your universal set. Okay. So this is measurement-based quantum computation in a nutshell. Any questions? Yes?
Do you need to have like decisions made in real time after you measure?
Yes, you have to. And this is the last topic I want to talk about. Yeah? So the randomness of the measurement outcomes, it must go somewhere. If that was never used, I mean, the outcome was never used, then this would basically be like tracing over, and that is not going to get you anywhere. So you need to make decisions real time. I hope I will be able to get to that.
It could also be that you just, in the end, you just look at all the results and you do some classical post-assessment.
Oh, yes, you do. Yes, you do that.
But it could still be non-trivial without even making adaptive measurements, right? I mean, in principle,
Yes, in principle, that could be the case, yes. But to the extent that I can explain it, those measurements would not be local. Mm-hmm. Yeah.
So, with respect to this measurement with angle alpha,
Yeah.
so I need to have the resource of measuring in any angle?
No, it's not necessary. It's not necessary, and that will be important for fault tolerance. So it would suffice if you were able to do the measurement right in the middle between x and y. So you might call this an angle pi over 8 or pi over 4, depending on your conventions. That would suffice. That gives you the simulation of a universal set of gates. And for fault tolerance, this is actually important. Okay, so I continue, before we get into the technical things, I continue with a few characteristics of measurement-based quantum computation. So measurement-based quantum, here's something that's not so good about it. Let me start with that. Measurement-based quantum computation is a little bit greedy in terms of qubits. And this has to do with the very construction. So in the circuit model, you need the qubits in your quantum register. But in measurement-based quantum computation, the number of qubits involved is basically the size of your circuit. So there's more qubits involved. Okay, there's all techniques of mitigating this effect. So you could reuse qubits. You build a bit of cluster state, measure, and then these measurement qubits become free and can be used to attach more cluster on the other end. So these conveyor belt techniques exist in all sorts of varieties. This is something that you can do to mitigate the qubit count. And yeah. And if you are from PsiQuantum, for example, then you will be thinking about ideas of creating cluster states slice-wise or in smaller chunks. Good. Yeah, so talking about PsiQuantum, Terry Rudolph. So measurement-based quantum computation is good of practical relevance, whenever you have a computational scheme that relies on probabilistic heralded entangling gates. Yes? Such architectures exist, most notably quantum computation with photons. And then measurement-based quantum computation is very, very useful. So if you talk about photons, then the standard scheme of doing it today would be the Knill-Milburn-Laflamme scheme, KLM. And when you start with that, measurement-based quantum computation reduces your overhead really significantly. Yeah, so that's maybe also a practical viewpoint to keep in mind. So then there's work by Anne Broadbent and Elham Kashefi and Joe Fitzsimmons. So there is a scheme for secure delegated quantum computation that has MBQC running underneath. It's an algorithmic application of measurement-based quantum computation. And finally, so measurement-based quantum computation is good for distributed computations because, as we learn next time, 3D cluster states are inherently fault-tolerant resources. Yeah, and you can stretch them out over space. Good. Okay, so much the introduction. So general comments. So now I'd like to get a tiny little bit technical. So let's define cluster states. They came up so much. So let's see what they actually are. And so here is one particular way of creating them. So it's just a very short procedure. So let's just go through them. And this creation procedure we will use later in a few proofs. So it's actually going to be of use today. So it's just a two-step procedure. So we begin by preparing a product state of qubits in an eigenstate of sigma x. Yeah? Just the equal weighted superposition of 0 and 1. Okay, this should be easy to do. In the second step, there's only a second step, and that's it. We switch on an easing interaction and evolve according to it for a finite amount of time. And that amount of time is always the same. It doesn't matter on the geometry of the cluster state or the size of the cluster state. It's always the same. Yeah? The stronger your interaction strength, the shorter the time. Now, this is the condition. So it's independent of size or shape. Okay, so this is how you create a cluster state. And please, if there's questions, please just make yourself heard somehow. Yes?
So suppose I make an error of epsilon in T in every one of my qubits.
Yes.
How big is the disaster? Is it a disaster?
Yes, it would be a disaster for the universality proof because the errors would add up. A little mismatch in the interaction time would lead to a logical error, and these errors would add up. That would be bad. Like in the circuit model also, you have errors adding up. That is not a good thing. And the effect would be the same here. Would be exactly the same here. So for that we have fault tolerance. So if the same happens in a 3-day cluster state and you have error correction running, then that time mismatch is just part of your error budget, and you just need to be below the threshold, or from the practical point of view, you want to be significantly below the threshold. But then it's not a problem. It's not a significant problem anymore. Yeah. But in 2D, without error correction, it would be a problem. It would ruin your computation over time. Like in the circuit model, if every gate is a little bit erroneous, it ruins your computation after a while. It's completely the same here. Yes?
When you say this computation is fault tolerance, you mean this is fault tolerance even if I made wrong my cluster state, as you saw in the previous slide?
Mm-hmm.
Instead of time t, I put t plus epsilon. And
Yes.
now I have error of my initial
Yeah.
state.
Mm-hmm.
Also fault tolerance for this. How much pure versus your cluster to be?
How? Excuse me?
How pure you need your cluster to be?
How pure?
Instead of pure cluster, the error of the cluster itself.
Yes. Well, with respect to an error model that I do not want to explain right now, you can afford 1% of error, or let's say 0.8% of error per operation that is involved. And that in this here, what counts here is the preparation, the entangling gates, the measurements, the wait times. Yeah. But we will talk about error correction. Yes?
Are you applying the Ising only every 2 neighboring qubits or another scheme?
In the cluster states that I am using, yeah, so, well, the Ising interaction is always applied where we see a line here. Yeah? So that is the geometric convention. So, yeah. So here, these are one-dimensional, so it is indeed nearest neighbors. Here, this is not exactly a regular grid. Yeah, but wherever the lines are, the Ising interaction is applied, and that matters.
Equivalent to control Z, right?
Yes, yeah, and that is a fact that we will later use. The Ising interaction is equivalent to a conditional phase gate, and that will show up in some few simple proofs in a few moments. Thank you. Good. So yes. So small cluster states are already known. We know what they are. So this is, I should say, is modulo local unitaries. This is equivalent to a Bell state. This is equivalent to the Greenberger-Horn-Zeilinger state. So we know these already. Here's another simple arrangement, gives you a code word of the Steen code. So cluster states come up in various contexts. Just wanted to point that out. And now comes the definition. So in many ways, especially when we talk about quantum error correction, this will be beneficial. Cluster states are stabilizer states. And so we define them through their stabilizer. So let's see what the stabilizer generators look like. As was just explained, everybody had a course on quantum computation here. Was the stabilizer formalism part of that? Yeah, I see nodding. Can you kind of knock somewhere if you have not heard of the stabilizer formalism before?
I think you could just explain it.
I could just explain it. Okay, let me then. Yeah. So we know, let me just say, if I have an n-qubit states, I have 2 to the n amplitudes. I don't want to write them down all the time. And there is a subset of states that can be very easily written down. So for example, the state plus that came up, sigma x eigenstate, yes, the state plus that came up before, I can define it as by this relation. I write it as the eigenstate of spin operator sigma x with eigenvalue 1. Up to global phase, this is a unique definition of the state. Let me give you another example. Let's talk about the spin singlet. Let's call that B11. So this is spin up, spin down, minus spin down, spin up. Yeah? Very important state. So this is also a stabilizer state. I can now define it. I have 2 qubits now. I can define it now by 2 such relations. So let me just write them down. So sigma x on particle 1 tensor sigma x on particle 2 times my Bell state. In this case is, we have an eigenvalue -1. Yeah. Okay. And there's another relation. Okay. Good. I'm explaining it through an example. So you see, just first thing to note, you can define certain quantum states through relations like this, through eigenvalue, eigenvector relations. Okay, so just, of course, this is completely equivalent. They define the same state. I should say these 2 relations define that state uniquely. All right, you may ask, okay, can be done. Well, what's the point? And the point is when you go to large numbers of qubits, the effort that it takes to define such a state. So if you have an n-qubit state, what you need to write down for the states to which this applies is n relations, n qubit states, n such relations. That's an efficient way to describe a state. It has 2 to the n amplitudes. If you want to write down all these amplitudes, this might be much more, it will be, in general, much more complicated. So you have a tremendous gain in efficiency. This is a linear-sized description in the quantum state. And that is part of the stabilizer formalism. And then, there's lots more to it. I just wanted to say it's an efficient way to describe quantum states. It doesn't apply to all quantum states, but when it applies, it is very efficient. And the cluster states are states of these kinds. And so what we need to figure out is what are the counterparts to these operators here for the cluster case. Yeah, and they are given here. They all look the same. So we pick a site. So this is our lattice where the cluster state lives. We pick a site. And now we place on that site a Pauli spin flip operator sigma x. And we place sigma z's on all the neighbors. Then we take the tensor product of these operators. Yeah, so this is it. So this gives us our one generator for the stabilizer of the cluster state. And then we have the same thing for any site here in the lattice. Yes?
Is it true for qubits? For a qubit?
Yes, for a qubit, yeah. Yes, so for the qubit, there is a similar, there is qubit generalizations of cluster states. So people, yes, so the number does not depend on the dimension. It does not depend on the dimension, only depends on the number. At least this should be true for prime dimensions. Non-prime dimensions, maybe there's more to say, but yeah. Yes. Yes, they all commute, and you can kind of see it. You can convince yourself of that. Yeah. Yes.
Do you assume boundary conditions, or do you take?
Yeah, on the boundary, these guys look a little different. So, for example, let's go to the corner. Okay, it goes on here and here and here. And so on the corner, there would only be 2 neighbors. But commutation would still work out. Yeah. An easy way to see why the commutation works out is, let me not get into it. We can talk about it later. Good, because I need to be a little bit mindful of time. Good, okay, just briefly about early experiments. I mean, the chief experiment to mention would probably be PsiQuantum, but we don't know what is going on in their labs. So instead, here are 2 early experiments. So the first laboratory that created cluster states was Emanuel Bloch's laboratory, and this was with cold atoms in optical lattices, and this was early 2000s. The first experimental demonstration of measurement-based quantum computation is not much later. It's from 2005. And this is Philip Walter and company. This is already with photons. Yeah? Good. And what did they do? They did, well, a universal set of gates, small cluster state, an instance of Grover's algorithm. Good. So this is what I want to say about experiment. And now, in the remainder of this presentation, I want to go through parts of the universality proof. We will not have all the time to go through the proof in full, but we can do a few parts. Good. So let me just remind you, I want to explain this, why all this measurement amounts to a computation. Okay, and so here is what we have to prove. There's 6 things. I mean, the first we wouldn't really need, but maybe it's assuring that you can do the identity gate. Maybe it's just as a warm-up, that is something worth doing. Well, then 1-qubit rotations are part of a universal set. So we want to know, how do we do 1-qubit rotations? We want to know, how do we do CNOT gates? They are also part of a universal set. And then, okay, you know, there's lots of stuff missing. The cluster state has all these qubits here, so how do we get rid of them? So that's also something we need to check. We need to have a way of removing qubits that are not needed for the computation. We have to talk about composition. Yeah? When we combine 2 MBQC gate simulations, we want to check that they combine in exactly the same way that the gates themselves compose. And finally, and this was already mentioned a little bit, classical site processing and so forth, how do we deal with the randomness of measurement? So this I really would love to talk a little bit about, but we need to see what we actually have time for. Good. So of these 6 items, I want to talk about these 3 here. So just with this, starting with the very simplest, then proceeding to 1-qubit rotations, skipping all the rest, and then talk about mitigating randomness. That's the plan. Okay, so let's get started. Okay, so we just want to explain, it's the very first thing, the identity gate. How do I do the identity in measurement-based quantum computation? So what would that be? We would be looking at a cluster state with a quantum input. This is something we have not yet defined. I'll define it in a moment. And we want to show that by measurement, we can shuttle this input from where it started to the last site in the chain. Okay, so that's maybe a simple thing to do. So now what is a cluster state with an input? So we already mentioned that cluster states can be created from a product state of eigenstates of X with the Ising interaction. And our computer science way of talking about the Ising interaction is conditional phase gates. So if that state was a plus, then this procedure would be just the creation of a cluster state. Now, this first qubit here is not in a state plus, it's in some general quantum state. And in that case, this procedure we call a cluster state with input. Cluster state with a quantum input. Yeah. Okay, so that's the preparation part, and then come the 2 measurements. And what we want to show is that this whole procedure, modulo some classical site processing, brings out this quantum state down here at the bottom. And the way we are going to show this is by relating this to teleportation. And it's a very important connection that measurement-based quantum computation has with teleportation. So let's just see that. Okay, so what I'm doing now is I take this circuit and modify it by simple equivalence transformations such that we get the teleportation protocol. So let's do that. Okay, so going from here to here, we just insert the identity in the form of two Hadamards. That's the first thing. Next thing we do is we propagate those measurements here in the end past the conditional phase gate and past the Hadamard. That's again stabilizer stuff. So you can convince yourself that this sigma x, when it is propagated backwards, gives you x tensor x, and this sigma x, when it's propagated backwards, gets you a z tensor z. So now you, under backward propagation, you get a non-local measurement, and well, we have it right here. When you see, those observables define Bell states, and so what they amount to is a Bell measurement. So these two measurements are nothing but a Bell measurement. Also, this part here is the preparation of a Bell state. Yeah? And then what happens after the Bell measurements on the first two qubits is irrelevant for the remainder of the protocol. So this is really, well, your quantum state of input, a Bell state, a Bell measurement. So this is the teleportation protocol. Good. Okay, so much for that. That was the simplest thing to show about measurement-based quantum computation. And we move on with something along the same lines, or similar types of arguments. And we want to now explain the rotations. Again, we look at a simple system. We have 3 qubits. The conditional phase gates create the cluster state with input, and then we have 2 observables that we measure. And we will specify them in a moment. But first, let us simplify the situation. So what happens when going from here to here is we just rearrange commuting operations. Yeah? We move them back and forth, and with commuting operations, we can do that. Yeah? So this measurement commutes with that conditional phase gate simply because it acts on different qubits. Okay, so we can deform the circuit slightly into this shape, and then we see, oh, yeah, we have the same building block here appearing twice. It appears here, and it appears here again. So we can simplify the situation and just look at one of these building blocks and combine them later. Okay, so let's do that. Let's just look at these building blocks, what they do. Okay, and also we now specify what these observables are. Previously we left them open, but now we say these are Pauli operator sigma x conjugated by some unitary of this form. Okay, and so then this measurement is equivalent to having this unitary right before an x measurement. It's the first equivalence. So the next step is, okay, there's a conditional phase gate, unitary about the z-axis, they commute, and so we can move this unitary to the other side. Okay, and so this is just the first thing that happens. We have our unknown quantum state, we have a unitary applied to it, so this is that, and now we only have to figure out what this 2-qubit operation does. So we have an incoming quantum state, an ancilla, entanglement, measurement of 1 qubit. Okay, so what this part here does, I leave that to you. It's a 2-qubit exercise. Yeah, maybe you can do it later if you find the time. And so what it does, what this thing here does is a Hadamard gate, and then there is an outcome-dependent correction. So the outcome here of this measurement does matter. It does matter, and it has this effect. It creates what we call a byproduct operator. It's an outcome-dependent Pauli operator. Okay, so this is the effect. This is the effect of randomness of measurement outcome on the computation. And we don't want this thing to be there, but it is there, and we have to deal with it. And if I find the time, maybe I can tell you a little bit about it. I think we will at least can begin to talk about this temporal order business, but S is a 0 or 1. Oh yeah, sorry, that's a very important point. So the eigenvalues are of course plus minus 1, and yeah. So let's call this the eigenvalue of the measurement. Our convention is like this. So when the eigenvalue is plus 1, this means S equals 0. And when the eigenvalue is minus 1, this means S equals 1. Thank you, that's a very important clarification. Yeah, okay, so this is now our logical building block. This comes from a piece like this. And the Hadamard turns out to be very important. For when we now combine two such things, then a little bit of algebra, because of, the Hadamard conjugates Z and X, so Z becomes an X, and so on and so forth, we get this. So, the second rotation is now about the x-axis, not about the z-axis. The first rotation remains about the z-axis. And then we have two of these Pauli corrections also with Pauli x and Pauli z. But the important point is we can now perform rotations about the z-axis and the x-axis. And then maybe Euler decomposition comes to mind. By putting together rotations of this type, we get any rotation in SU2. Okay, final point. Because of those Hadamards, the Z and X rotations alternate. So the measurement procedure would be the same for Z rotations and X rotations. Whether it's a rotation about the Z-axis or the X-axis is a matter of where the qubit is located that you measure, whether it's on an even side or on an odd side. Good. Okay, I think this is all I had to say about rotations. Are there any questions?
But has that been fed? How do you guarantee you get the rotation you want? I'm missing something. You measured S and S prime.
Yes.
Now you're telling me that's what you get.
Yeah.
But this, how do you get the rotation?
How do you get the rotation? Where do you get the rotation angle, you mean?
Oh, you have to go back and put the rotation angle in after you get S.
The rotation angle is in the measured observable. Yeah? So, let me go back. So you see, this is the observable that's being measured, and it depends on an angle alpha. Yeah. So the observer, by choosing your measurement basis, you put in the rotation angle. If you chose another measured observable, the rotation angle would be different.
Got it. But there are still four possible outcomes.
Yes. Yes.
Yes. Yes. Yes.
So do you get different rotations?
Yes.
That's what I'm missing. It's very old.
Okay. So yes. Okay. So this is what you get, irrespective of what these outcomes are. And but then you have these pieces here that you don't want to be there. Okay, you know what? In my remaining time, I skip right to that problem. Okay, so there were all these other steps. Let's just forget about them. Let's just move right into that topic. Yeah, because I was not going to say much about these intermediate steps anyway. I already mentioned them. I'm happy to say more. But really, this temporal order thing, this is kind of funny. Yeah. So the problem that we have to deal with is that when you make a quantum mechanical measurement, you can choose the basis but not the outcome. And that gives you difficulties here in this computational scheme. I mean, not a fundamental difficulty. It can be overcome, but you need to deal with it. And so now let's talk about that very thing. Okay, so this is what we've just discussed. So you measure your qubits in a chain, and yeah, so in the circuit model equivalent, what this does is you get your rotations as you planned, but you also get these additional pieces depending on measurement outcomes that you don't really want, but they are there, and so you have to deal with them. Yeah? And so here, let me be a little bit specific. So again, these are the observables that we measure. These are the rotations that we simulate. Okay, good. So now this remainder of the presentation is how do you deal with that stuff? Okay, and so the overall idea is to propagate them past the end of the computation because, well, whatever happens after the final measurement doesn't affect the computation anymore. So that is a safe place. So now we need to see what happens in the course of propagation. And I do it here in an example. So let's just consider one of these byproducts, we call them. So suppose the outcome was 1, we got this thing here, and now what do we do with it? We propagate it out like this. The first step of propagation. So what it technically means is that we have conjugated this gate under this Pauli operator. And what that means is the rotation angle is flipped, yeah? X and Z anti-commute, so the rotation angle is flipped and not good. We have just changed our rotation angle. So next step is exactly the same, but now the x of the rotation axis and the sigma x here commute, so nothing happens. Do this again. So again, we get the rotation angle reversed. Not good. Need to deal with that. Okay, then we move it past the measurement. It commutes with the measurement, so nothing happens here, and then we send it off. What happens after the final measurement doesn't matter. Okay, and so the effect that we saw in this forward propagation was this flipping of angles, flipping of rotation angles. And that is the thing to deal with. So here you have this relation as a formula. So you find that, yeah, so this is where the Pauli X originated in qubit 2 in our example. This is where it caused the effect. So that's why you have qubits 2 and 3 here. There's nothing particular about those, but just this pair matters. Okay, so the rotation angle, the angle about which you rotate in your circuit model simulation, is the angle that you measure in times this correction depending on the outcome. Okay, and now you can move the -1 to this power to the other side, which is of course mathematically equivalent. Okay, and this is how you should read it. Yeah, so the measurement angle, not the rotation angle is adjusted to the measurement angle, but the other way around. The measurement angle is adjusted to the rotation angle. So, yeah, so you choose the measurement basis for qubit 3 only after you have learned what your measurement outcome at qubit 2 was. This is how you adjust, which means qubit number 2 must be measured before qubit number 3. And this in fact gives you the temporal order. So the randomness of measurement in quantum mechanics is completely linked to the temporal order in measurement-based quantum computation. Good. I love this subject, so I could talk about it for hours, but not here. Okay, I think I'm coming near the end of my lecture. So I just wanted to reiterate, qubit 2 must be measured before qubit 3. And so it is, I said this also, so I'm just summarizing. So the randomness in quantum measurement implies the temporal order in measurement-based quantum computation. Is the temporal order different? Yes, it is different from the order in the circuit model, and this is because there's two measurement bases, the x and the z bases, that are not changed as bases under these flips. Yeah, the x basis remains the x basis, the y basis remains the y basis, and therefore, everything that is measured in the x and y basis needs no adjustment and just drops out of the temporal order in measurement-based quantum computation, and this is the entire Clifford circuitry. So Clifford circuits or Clifford subcircuits are done in no time. Good. I think this is what I wanted to tell you. I told you a little bit, here's a summary, told you a little bit about the universality proof. Coming up is fault tolerance. And here there's a few references if you want to read up on the subject. Thank you. Good. I hope I made it in time.
Any questions?
There was a question over there. Yes?
Yeah, so you said that the is important, but do you really have to adjust the angles during the computation, or can you just on the end of the computation explain your results by the data the angles?
No, it is the former. The scheme that I described, you really need to adjust every measurement basis except x and y according to measurement outcomes you have obtained earlier. So it's really in time, during the course of computation, that you need to adjust measurement bases.
First was very interesting lecture. It seems like you need to have some classical computation to actually decide how you're going to fix things after you.
Yeah.
And my question is, if there is an upper bound over the time that your classical computation needs. In particular, it's interesting because if you think about that, if you do not have any restriction, then you could just simulate some protocol and then have all your continuously free. So for that model to be really something that means something, it's important to say something about how much you can expand.
Yes, I can give you the answer. So the classical computation that you have to do is computing parities. It's just addition modulo 2.
Right.
And the worst number of bits you could ever be afraid to add up is the size of the cluster. Okay. Yeah. And so addition modulo 2 can be parallelized. You just, like in a soccer tournament, you have this exponential tree. So the time it takes is proportional to the logarithm of the size of the cluster.
Okay. Okay. Thanks.
I have a question.
Yeah.
Suppose I have a quantum circuit
Yeah.
consisting of gates,
Yes.
which are, I could draw a picture of.
Yeah.
And now I would like to run it in your scheme.
Mm-hmm.
I have to compile that
Yeah.
into measurement-based.
Yeah.
And what is the dependence of the size of the measurement-based code and the number of qubits on what I put in? Does that make sense, my question?
Yeah, I think so. Well, you're asking me about how hard a computation it is to convert the circuit into a measurement pattern?
Just not how, no, just how many qubits, how many measurement qubits.
Yeah.
Yeah, how many steps on that?
Yeah. Okay. So I need to check I had a CNOT there. I think it had a block length of 7, although I'm not 100% sure, and the height is, 7, and don't nail me on those numbers. Yeah, so the next qubit, next logical qubit would be at a distance of 2, and the next slot for gates would be at a distance of 6. So you have a tile of size 6 times 2, and this is where you fit in a gate. And that could be a C0, or it could be a 1-qubit rotation. Yeah. And then it's just kind of straightforward mapping from the circuit to the measurement pattern. Mm-hmm.
Sean, yeah.
Can you please elaborate a bit about the advantages of this? We saw the universality, and before we go to the fault tolerance, specific advantages for this implementation of circuits.
Yes, so the most striking practical application is in linear optics quantum computation, where it reduces the overhead. Yeah? So then another application was N. Broadband's secure delegated computation. Although I think you can do this in a circuit model just as well, but it was conceived in the measurement-based scheme. So in the end, I would say if you're looking at it from a practical angle, then yeah, it is quantum computation with probabilistic heralded gates. There, it really buys you something.
Thank you.
Okay.
How do you perform arbitrary basis measurements?
Arbitrary basis measurements?
So you need to measure in some arbitrary basis.
No, I mean, not arbitrary.
But some not.
Yes. Say what you need to measure in is, okay, if this is your Bloch sphere, you need to measure, say this is x, this is y, and this is z. Yeah? You need to measure the poles. Yeah, that's what you need to do. And then on the equator, maybe the entire equator, if you don't want to do that, at least x, and in the middle between x and y. This is what you need to do. How you do it? No, these are Hermitian observables. This is what I say as a theorist. How the Hermitian operators, excuse me, and how the experimentalist does it. I don't know. I mean, I would know a little bit, but yeah.
Yeah.
Yeah, so maybe somehow to connect my friend here, doesn't the time modeling constrain you a bit with regard to usefulness in parallel computing?
Well, I mean, what I want to say, I mean, in the circuit model, you have time ordering too. You know, and this is just quantum computation.
You introduced an advantage, essentially, in this model, right? With regard to parallel computing, or should I say,
Yeah.
distributed computing, right?
Well, the temporal order in this computational scheme is more flat than in the circuit model. You have temporal order remaining, but it's less temporal order than you have in the circuit model. Yeah? So that's what I can say about that.
Can you explain this?
Yes. So this was the point I made in the end. So whenever, you know, we have this flipping of measurement angle. So here is, let's say this is the x direction in the Bloch sphere, this is the y direction, and this is the direction along which we measure. You know, and we saw these factors of -1 coming up. So depending on what your measurement outcomes were before, you have to flip your measurement basis. And now there is bases that are invariant under this flipping. And this is the x basis for which this angle is 0, and the y basis for which this angle is pi/2. Yeah, these bases are invariant under flipping, and so you don't need to adapt physically. You can do the measurement right away. And then, well, you ask yourself, oh, what gates do I simulate with x and y measurements? And it's exactly the Clifford circuitry, you know? And that totally drops out of temporal order. You know, they take no time. Can be done, no matter how large, can be done in one round of measurement.
Okay.
Yeah, so just a small question. You have the canonical example of the slide that you returned to a few times with the
2x2 grid with
Yeah.
so you do some.
Okay.
Yeah, this one. So you do some like routing here of taking the second qubit down and then back up. CNOT's config.
Yeah.
Is that it? Like it's just.
That is it. That is exactly it.
So you need 1.5 spaces for each.
Yeah. No. We've improved. We have improved. This is the first CNOT that we found. We have this other CNOT. Now I need to go all the way back. All right, let's see. We have this other, now, a little bit later, we found this other CNOT. And you see, it is not as high. Yeah,
So now you just have straight lines for.
Yes.
Okay. Thanks.
Any more questions?
Yes, but that's not.
Did you think of using anything else than cluster states as well?
Yes. Yeah. So this is a work that I'm very proud of with my.
Could you repeat about the question?
Yes. Did you ever consider other resource states than cluster states? Yeah. So maybe the thing I would like to say most. Yes, we considered the AKLT state. This is work with my former postdoc Tzu-Chi Wei and with Ian Affleck. So the AKLT state in 2 dimensions, so the spin 3/2, is also a universal resource state. So it's a rather complicated procedure to show. Not as straightforward as this. But that is also a universal resource. And then this question also ties in with what I'll say in my last lecture. Now we know that there's entire phases, symmetry-protected phases of universal resource states.
Could we see again the slide with the references?
Yeah, and maybe the slides will be posted. I don't know, could potentially be. Yeah.
Have access to this. I have some technical questions. So when you show this, the latest kind of this gate,
Yeah.
you show the slide.
Yeah. It's here, for example.
Which one is this?
This is the control knot on the left.
How do you compute this? How did you find this? This is a computation I can do by hand on a finite piece of paper?
Yes, on a very finite piece of paper, you need a theorem. So there's a theorem that we proved about correlations. So let me just sketch it. And we could do this over coffee. I mean, not proving the theorem, but applying the theorem. And so we single out the input, on the left, and the output on the right. And now we have, we say we have a cluster state here, and then we measure in Y and whatever we measure in, And this will create a stabilizer state. And then we check what the resulting, after measurement, we end up with a 4-qubit state, like this. And we check its stabilizer. I mean, these types of operators, what will they look like? And from those operators, we can infer the gate action. Yeah? And
I'm asking it reverse. Like, suppose I didn't know it is y, and x. I didn't know. Then I would have 2 to the n choices to make. I would get crazy.
Yes, but yes, there is no algorithmic procedure. So this is really, you build an intuition, and then you'll be faster than checking out all the 2 to the n choices. Yeah, it is a little bit of witchcraft still. There's no procedure for creating these gates.
Because Euler would say mathematics is what you do after you guess right.
Yes, that's an instance of that for sure.
Okay.
Thank you.